This video begins Unit 19, Cardiovascular Physiology. It includes Part A, Pressure and Flow, Part B, Characteristics of Cardiac Muscle, and Part C, the Cardiac Cycle. Being rather complex, this unit consists of 5 videos. This one is the first over these 3 parts. Video 2 includes Part D, Video 3, Part E, Video 4, Part F, and the last video, Part G and Part H. Part A, Pressure and Flow. This is a look at the relationship of pressure differences to flow of fluids. If a pressure difference exists, the fluid will flow. Now, in biology, fluid is a liquid. I know in physics, a fluid is a gas or a liquid. Fluids flow from high to low. You're going to hear me say that many times. Consider a syringe. If the plunger is pulled out, the volume inside the syringe increases, but that causes a decrease in the pressure as long as no air is allowed to move into the syringe. If the pressure in the syringe is less than the pressure outside, air will flow in from high to low. If the plunger is pushed in, the volume decreases, the pressure increases, and if there's a connection, if the pressure in the syringe is greater than the pressure outside, air will flow out. Flow is from high to low. That's a basic idea. It actually is called Boyle's law, and we'll come back to it in some detail when we get to the respiratory system. Pressure differences are determined by 2 things. One is the pressure that's generated. If you take a closed container, but fit one side of it with a piston, if you push that piston inward with a given pressure, pressure inside will be generated equally on all parts of the walls. If you take that same container and attach a tube to it, so it's open to the outside, the pressure difference will result in a flow of fluid. After all, fluids flow from high to low. By the way, moving fluid technically exerts no pressure. When you take someone's blood pressure, what do you do to the flow of blood? You stop the flow. The greater the pressure difference, the greater the flow. The other factor that determines pressure difference is resistance to flow. One factor there is the viscosity of the blood, the thickness of the blood. If you have 2 containers, each fitted with the piston, and you apply the same pressure to both containers, the high viscosity fluid will flow out slower than the lower viscosity fluid. Imagine a squeeze bottle with water in it and a squeeze bottle with syrup in it. You squeeze both of them, the water squirts out very well, the syrup just sort of oozes out. Another factor is the radius of the tube, or the diameter, that is, how big the tube is. If you attach 2 tubes to the container, one with a smaller radius, the other a little bit bigger, and you apply the pressure, the fluid will flow easier out of the larger tube. Now that's not so intuitive, because you imagine you hold a garden hose, you're running water through it. When you squeeze the hose, the water squirts further. But in this case, we're talking about 2 tubes in parallel with the same pressure forcing the fluid. Another factor is the length of the tube. The longer the tube, the more friction between the fluid and the wall of the tube. The water flows out easier through a short tube than a long one. Imagine if you had a garden hose that was 3 feet long You turn on the water and it squirts out easily. But imagine you had a hose that was maybe a mile long and you turned on the faucet. Water would probably not flow out the other end because of the great resistance. Let's look at resistance a little more. Here are three tubes. Which of these three would provide the best flow? The top tube is one with no resistance. You would think the fluids would flow very easily through that. But notice, with no resistance, there's no pressure drop. So the pressure at the exit end is the same as the pressure at the entrance end. So there'd be no flow. The bottom tube, you might say, would have the best flow because there's a big difference in pressure, high resistance. Yet, in this case, the pump has to work too hard to get the fluid moving. So the middle tube is the best. There's a difference in pressure from high to moderate, so fluids will flow from high to low, but the pump doesn't have to work too hard to accomplish this. Let's look at the system in a little more detail. We'll look at a circular tube. The circular tube represents the design of the cardiovascular system. In order for fluids, that is blood, to flow, a pressure must be generated. That's what the heart does. And a pressure difference must exist. Here are some questions about the donut arrangement. Let's apply pressure at point P and answer the question, does fluid flow in a rigid tube? No, it does not, because the pressure in a rigid tube would be generated equally on all parts of the inside of the wall. Does blood flow in an elastic tube? Yes, it would, but it flows in both directions. What will happen to the flow of fluid in the elastic tube if we have valves in the tube? Fluid will flow in one direction because when it flows backwards, it forces the valves close. Where are the valves in the cardiovascular system? Well, right away you'll say, in the heart. That's correct. But there are some other valves. Where are they? They're in the veins of the body. Note that the elastic tube expands and the valves prevent backflow. What maintains the circulation at point A in the elastic tube with valves? The elastic recoil of the tube. This is a critical idea that we'll come back to on many occasions as we progress. Let's look at part B, characteristics of cardiac muscle. Cardiac muscle is similar to smooth muscle and skeletal muscle, but it has certain unique characteristics. One characteristic is it exhibits automatic contraction. We call that myogenic. The heart does not have to be hooked up to the nervous system in order to beat. If you were to take carefully a heart out of a live turtle, let's say, put it in a beaker of saline solution that was isotonic to the turtle's body fluid, that heart might continue beating for minutes or longer, all by itself. The heart has an inherent rhythm, a built-in rhythm, and it exhibits all or none contraction. That is, when it's stimulated to contract, it contracts all the way, or it does not contract at all. It has a long refractory period when the muscle cannot be re-stimulated. The refractory period is different. In the atria, it's 1/10 of a second. In the ventricles, the refractory period is 3/10 of a second. The absolute refractory period is a period when the muscle cannot be re-stimulated, no matter how strong the stimulus is. In the ventricles, this occurs between the beginning of the QRS part to the peak of the T in the ECG. Now, I know that doesn't make any sense right now, but we'll get to it shortly. The atria act as a single muscle, and the ventricles act as a single muscle. So when the fibers of the atria or ventricles contract, they all contract as a unit. The stimulus for contraction of cardiac muscle may be the nervous system. It may be the endocrine system by way of hormones. Or contraction may be spontaneous. That's that built-in inherent rhythm we talked about. The fibers of cardiac muscle are branched and interconnected. They're linked by discs called intercalated discs that are composed of protein fibers and gap junctions. They are junctions that join one cell to another. They generate energy by aerobic metabolism. At rest, the percentage of energy that is generated by cardiac muscle, 60% comes from the breakdown of fatty acids, roughly 35% from glucose, and roughly 5% from other sources. Fatigue in cardiac muscle is absent. Now remember, calcium is needed to uncover the binding sites on the actin and initiate contraction. The heart is very sensitive to extracellular calcium. A small amount of calcium from the extracellular fluid triggers a large release of calcium from the lateral sacs. Therefore, contraction of cardiac muscle is strongly dependent on extracellular calcium. All right, let's look at part C, the cardiac cycle. This describes the events in a single heartbeat. We'll look at heart rate and stroke volume. We'll look at systole and diastole, heart sounds, pressure in the ventricle, volume, and valves in the ventricle. Let me give you some terms first. Heart rate, HR, let's say is 70 beats a minute. Now I'm going to round off these figures for purposes of clarity, hopefully. Stroke volume, SV, is roughly 70 milliliters per beat by each ventricle. Chronotropy is a change in heart rate. Ionotropy is a change in force of contraction. The average heartbeat at rest lasts roughly 0.8 of a second. Systole is contraction, and diastole is relaxation. Atrial systole occurs in the first tenth of a second of the cardiac cycle. Ventricular systole occurs in the second, third, and fourth tenths of a second of the cycle. Atrial diastole occurs from the second to the eighth tenth of a second in the cardiac cycle. And ventricular diastole occurs in the first tenth of a second, as well as the fifth, sixth, seventh, and eighth tenth of a second intervals. Notice that the heart rests more than it works. The heart makes two sounds, lub-dup, lub-dup, lub-dup. Sounds are due to blood turbulence, valves opening and closing, and cardiac muscle contraction. First sound, sometimes referred to as S1, occurs after the start of ventricular systole. This is the lub sound. The second sound, S2, occurs after the end of ventricular systole. This is the dup sound. So you have lub-dup, lub-dup, lub-dup. Let's look next at ventricular volume. Number 1 represents a slight increase in ventricular volume from 140 milliliters to 160 milliliters. This occurs during the first tenth of a second interval due to flow into the ventricles from the atria during atrial systole. Number 2 refers to a period of time where there's no change in volume because all of the valves are closed. No blood is moving in, no blood is moving out. 3 represents a decrease in volume. This occurs during the third, fourth, and fifth tenths of a second interval. The flow out is due to ventricular systole. The ventricles are generating pressure, creating a pressure difference. Is the ventricle empty after the blood flows out? No, it's still half full. Note that there are 80 milliliters of blood present at the end of the 0.6, that is the 6/10th interval. Number 4 represents another period of no change in volume because flow is absent because all valves are closed. 5. An increase in volume to 140 milliliters occurs. This is in the 6th, 7th, and 8/10th of a second intervals. This is due to flow in during ventricular diastole. By the way, which ventricle does this refer to? It refers to both. Even though the left ventricle has thicker walls, the volume of blood has to be the same. Imagine what would happen if the left ventricle pumped more blood than the right. After a few heartbeats, the right ventricle would run out of blood. What is the role of the atria? Notice during the 6th, 7th, and 8th, 10th of a second intervals, the atria are relaxed. They're not pumping blood into the ventricles. The atria are collecting chambers. Collecting chambers. Let's now look at the pressures. First of all, atrial pressure. It ranges between 0 and 20 millimeters of mercury. Again, the numbers refer to the figure. Number 1 represents atrial pressure that's a little bit greater than ventricular pressure. This occurs during the first tenth of a second and partly into the second tenth of a second. This is due to atrial systole. Number 2, there's a brief increase of atrial pressure due to the ventricles contracting and pushing against the atrioventricular septum. Step 3, a gradual increase in atrial pressure occurs to the end of the cycle as blood flows in due to differences in pressure between the veins leading to the heart and the atria. 4, flow out in the middle of the gradual increase. This is due to a difference between atrial and ventricular pressure. What about the ventricular pressure? It ranges from 0 to 120 millimeters of mercury, quite a range. It's greater than atrial pressure in the third through the 6th tenth of a second interval. It's greater than aortic pressure in the third through the 5th tenth of a second interval. Step 5, flow in due to atrial systole. Step 6, ventricular systole has begun, but flow is absent because all valves are closed. Step 7, ventricular pressure is greater than aortic pressure. Flow will be out due to the ventricular systole. This is ventricular ejection. Step 8, ventricular diastole has occurred, but flow is absent because all valves are closed. This is isovolumetric relaxation. Step 9, flow in to the difference between atrial and ventricular pressure, ventricular filling. What about aortic pressure? It ranges from 80 to 120 millimeters of mercury. It decreases in the first and second tenth of a second interval due to flow away from the heart in the major arteries. It rises to in the third tenths of a second interval due to flow into the aorta during ventricular systole. There's a brief rise called the dicrotic notch. This is due to the recoil of the elastic walls of the arteries. Then it continues to drop as blood flows away from the heart. What about the valves? What's happening to the valves? Well, the valves don't have little motors in them. They open and close strictly because of pressure difference. Let's look at the AV valves, the atrioventricular valves. These are open when atrial pressure is greater than ventricular pressure, and they're closed when ventricular pressure is greater than atrial pressure. How about the semilunar valves? These are closed when aortic or pulmonary pressure is greater than ventricular pressure. They're open when ventricular pressure is greater than aortic or pulmonary pressure. Let's look in more detail. Before A, and after D in the graph, atrial pressure is greater than ventricular pressure. AV valves are open. The atrioventricular valves are open. Between A and D, ventricular pressure is greater than atrial pressure. The AV valves are closed. Before B and after C, aortic pressure is greater than ventricular pressure. Semilunar valves are closed. Between B and C, ventricular pressure is greater than aortic pressure. The semilunar valves are open. Here's a summary of the valves. AV valves close, aortic semilunar valves open at B, aortic semilunar valve closes at C, and the AV valve opens at D. So you see the differences in pressure cause the valves to open or close. And this is the end of the first video on the cardiovascular physiology. We're now ready to go to part D of Unit 19.